it will preserve the statistics of the actual distribution itself, and the algorithmic theorem will give you the expectation in as the iterations goes to infinity. But the problem with this is that MCMC in general can get stuck. So anyone who's ever used or like actually had to implement MCMC algorithms knows that for hard problems, this is not a fun thing to do. In particular, what ends up the most common issue that you end up having is that chains get trapped exploring local regions of high probability. So if you have a local region of high probability over here and a local region of high probability over here and a valley of low probability in the middle, you're most likely never going to actually make the traversal in the finite amount of time. So this is already problematic if you know there are multiple modes, but if you are working in a situation where you don't see them at all, by just letting your chain run, it may look like it's converged, but in reality, it's missed an entire chunk of the sample space, which could result in really poor estimates of your expectation. So in this case over here, it's initialized in the middle, and it found one mode, and then just over 10,000 iterations and never discovered the other. There's some other limitations that we have to work within. In particular, the biggest problem is algorithmic. A single chain is simultaneously responsible for doing too much. It needs to be both efficient at exploring the state space, but also simultaneously, it needs to be accurate. And both of these are kind of orthogonal tasks. So exploring the state space requires you to move around freely to see what's out there. Whereas to be accurate, you have to spend more time in the areas that are more likely. So often when you're running a single chain, it fails at both. And also there's a hardware limitations where the clock speeds in modern, in the last decade have kind of stagnated. So your processor from a decade ago isn't that much faster than it is now. So we can't really hope to run these chains for a significantly longer time. However, modern computation advancements have come from distributing computing. So running multiple threads in parallel. So we can leverage the hardware advancements to develop new algorithms. So in particular, our task or the way that we'll resolve this exploration versus exploitation problem with single chain is by running additional chains in parallel while delegating the task of exploration to a tractable reference chain and using a series of intermediate chains that are interpolating between the reference and the target, we can use those to communicate between the two. So this would potentially allow for the target to discover new modes based off of the suggestions of the reference. So that's the motivation. And so the platform for our algorithm is going to be annealing. So we're going to just go over, maybe some of you have heard of annealing as in the past, but we're going to just develop some terminology to see, just so that we're going to be using over and over again. So in particular, from now on, whenever you see pi1, it's going to be the target density. So this is something, think in the back of your head, something like the posterior distribution, which you can evaluate up to a normalizing constant, but not the normalizing constant itself. And pi naught will be our reference density. So this in the back of your head, think of like a prior, which is something maybe that's easy to sample from. Maybe you can get IID samples, and you can do so. And we're going to denote our bridge of distributions pi beta n as the annealing distributions. They are going to interpolate between the reference and the target. So the annealing schedule is going to be the sequence beta 0 up to beta n. So in particular, you can notice in this case where you have the reference distribution is a unimodal target, whereas the target distribution is this bimodal one. So as beta increases from 0 to 1, you actually have these, it slowly starts to deform from this unimodal to the bimodal target. The continuum of distributions, we're going to call the path. The most common example is what we're going to call the linear path, which geometrically interpolates between the reference and the target, or linearly interpolates between their log densities. So in particular, like you can see what's happening here, right? So the reference is this unimodal. So this y-axis is beta, and the reference is this unimodal target, is unimodal, whereas the target is bimodal. So essentially what annealing does is leverages the fact that the reference is tractable and potentially unimodal into building a bridge that connects the two targets, the two modes of the targets together. So this allows a path for the Markov chain to actually traverse from one mode to the other through the reference. So in particular, parallel tempering will be now, so the goal of parallel tempering isn't to construct a single chain, it's to construct a chain over a new state space that's enlarged. So we're gonna have a vector of states now that are, where the nth vector, nth component is gonna be targeting the nth annealing distribution. And we can recover our expectation of interest by just marginalizing out over the other non-target components. So the last component will always correspond to the target. So if we just look at the trajectory of that component, you end up recovering the same expectation of our interest. So we're going to construct this Markov chain by a two-step procedure. So first we initialize our states to whatever they are, and then we're going to perform a local exploration move. So the local exploration move, what this does is that it, at each component of our chain, we're going to apply a MCMC move that will be targeting the nth annealing distribution. So in this case over here, notice that we go maybe, so the first one, the state that's closer to the target, pi beta n+1 in this case, does not successfully traverse the mode, but it does stay within it and it's exploring within that mode. The chain that is, the state that's closer to the reference is successfully traverses the mode because it's a bit flatter. In particular, so after this local exploration move, we will allow for a communication to occur where we're going to propose swaps between the nth and the n+1 chain, where we're going to accept reject according to Metropolis-Hastings acceptance ratio. So this is the communication step is what makes parallel tempering. Because this is the situation where this is the step that actually allows for the different chains to communicate with each other and hence potentially allow for information from the reference to actually percolate to the target. So in this particular case, notice that if the swap that we propose is successful, then in one iteration, even though you started off in the left mode here, you ended up in the right mode. And this happened because of the exploration that occurred closer to the reference, not the actual target itself. To see how this works in practice, in the same example that we had before with the single Markov chain, if we just run parallel tempering, well-tuned with 10 interpolating distributions, we actually get this as a result. So not only does parallel tempering discover both the modes, but it discovers them and like allows for the chain to actually traverse them regularly and often. So this adds a sense of reliability to the discovery of various modes that a single chain just kind of lacks. So this one diagram should hopefully be enough to motivate you that parallel tempering is at least interesting and worth spending a bit more time thinking about. However, there are some catch. Tuning parallel tempering is quite hard. I've left a lot of details under the rug. In particular, how do you actually propose these swaps? I told you what a swap is, but not necessarily the optimal way of figuring out how the communication to occur. How do you actually pick the annealing schedule itself? Because I just said that these betas exist, but we don't know what they are. How do you pick the number of chains? That's not a well-designed problem either. How do you pick the path? So far, we've been assuming this linear interpolation between the log densities of the reference and the target, but in general, is that the best we can hope to do? And in particular, this is, so in particular, like, sorry. We also do not know when it's a hard problem or if it's just a bad implementation. So there's some problems that are just intrinsically hard and some that are where even in an optimal setting, we should hope to see bad performance just because of the difficulty of the problem. But then there's also problems that may be actually not that bad, but the poor performance is due to our implementation. So the state of the art before the topic of my thesis was you pick these swaps at random. So you put a blindfold on, you pick two chains and you propose a swap. And you do this over and over again until you hopefully have communication occur between the reference and the target. You pick the annealing schedule in a way where you reject 77% of swaps. For some people here who are in the Monte Carlo world, maybe have heard of the 23% rule that arises sometimes in MCMC. So that was, for reversible parallel tampering, this ended up being the state of the art, which seems unsatisfying because that means that about 77% of all communication should not occur, which kind of defeats the point of having good communication. You actually couldn't pick that many chains because there are some diffusivity reasons that came up where if you added too many chains, you actually got bad performance irrespective of the problem. So the rule of thumb was you start off with roughly 10 chains and you adaptively reduce until you get the 77%. How do you pick the actual path itself? The linear path is pretty much the only thing that's been used in the literature. And then finally, to distinguish whether it's a hard problem or a bad implementation, you're kind of just out of luck. There was not really much hope there was no real diagnostic tools that were developed for non-reversible parallel tampering. So for the rest of the talk, I want to kind of break it up into two sections, where the first one will be talking about introducing non-reversible parallel tampering, the main star of this show, where this was work that was introduced this was published in JRSSB last year. And we're going to be talking about what is non-reversible parallel tampering, how do you tune it, and what are the diagnostics that we can develop to actually efficiently implement this. And afterwards, we're going to spend another point talking about, the rest of the time, we're going to be talking about parallel tampering on optimized paths, which is work that was published in ICML last year. And this is where we're going to spend a bit more time going into the geometric aspects of parallel tampering and talk about how do you actually pick the path itself, an alternative to the linear path. This was jointly done with my supervisor, Alex, and as well as my co-authors, George and Arnaud at Oxford, and Vittorio and Trevor at UBC. So before talking about how do you actually optimally tune parallel tampering, the first question should be, what is the objective of parallel tampering? What does it mean to be a good implementation versus a bad one? So again, what matters for parallel tampering is the communication between the reference and the target. So what we want to maximize, we want to tune our algorithm to maximize this occurring. So we're going to say a round trip occurs when information percolates its way from the reference to the target and back. So this means that there's effective communication on both sides from the reference and the target. And notice how this is just one trajectory, but in general, we have n of them. So if we look at the total number of round trips across all the different trajectories, that will give us a total round trip. And so the quantity of interest that we're going to be optimizing is the percentage of iterations that result in a round trip, i.e. the round trip rate. So in this case, we could say that the round trip rate will be the expected number of total round trips by iteration t per unit time. So before talking about non-reversible parallel tampering, let's spend a little bit more time talking about reversible parallel tampering. So again, reversible parallel tampering is, again, you pick two chains at random and you propose a swap. That is the paradigm that has been the foundation of the PT literature. And as you can see, as you increase the number of chains, what ends up happening is that you actually start to get more of these squiggly, like Brownian motion type lines. And this we'll start to explore a little bit more in a second. But in particular, what this means is that when you propose two swaps at random, when information is going towards the target in one iteration, the next iteration, it can also potentially go backwards. So what this happens is that, what happens is that over time, you actually end up getting this diffusive random walk behavior. And the time that it takes for traversal to occur for a random walk across n iterations is O(n) squared, essentially. So it takes n squared amount of iterations to make one traversal from one round trip from the reference to the target. In particular, we were able to actually compute the non-asymptotic round trip rate in terms of so for a given annealing schedule and a given number of chains, the round trip rate for parallel tempering actually ends up equaling this quantity. So there's a 1/2n plus 2 times the sum of these odds ratio of the rejection rate. So the Rn is the probability that a swap is rejected between n and n plus 1, chains n and n plus 1. So notice over here, you get, you pick up a cost, when n is too small, these rejection rates are going to be quite large. So they're going to be close to 1, meaning that if even one of the rejection rates is off, is like it's poorly, if the schedule is chosen so that even one of the rejection rates is close to 1, then this term is going to blow up and your round trip rates are just going to tank. Alternatively, if you have too many chains, then this 2n factor is going to kill you and you're basically going to get bad performance. So in particular, so this quantity over here was non-asymptotic, but if you let the number of chains actually go to infinity, we're going to see that the 2n term over here actually dominates. And asymptotically, if you have large number of chains, you're always going to be decaying in round trip rate, and even in the optimal idealized setting. So in particular, reversible parallel tempering deteriorates with too many chains. And because of the fact that if you can't have too many or too few, this kind of creates this Goldilocks zone where you're at the worst, you're at the mercy of the worst of both worlds. You're kind of not really doing, you're not really able to leverage the structure of having a lot of chains. So this makes it very sensitive. The tuning of reversible parallel tempering makes it very sensitive. And the algorithmic implications of this is when you can't have too many chains running simultaneously, that means we can't actually leverage the massively parallel settings that we work in these days, for example, GPUs. The solution turns out to be algorithmically trivial. It's literally would be a 2-line change in your code. And the difference is instead of picking them at random, you propose them, you propose swaps that are even and then odd deterministically and alternate between the two. So what the odd swaps are going to correspond to is swaps that goes from, say, chains n and n plus 1 where n is odd. So in this case, this would be 1 to 2, 3 to 4. And then the even swaps would correspond to swaps that are proposed between chains n and n plus 1 where n is even. So where in this case, it'd be 0 to 1, 2 to 3, et cetera, et cetera. So in this case, like when a green cross is going to represent a swap was accepted. And so you're going to go from the odd swaps to the even swaps, to the odd swaps to the even swaps, and you keep going, and et cetera, et cetera. So this doesn't seem that substantially different, but turns out it has some really big implications. In particular, notice that if I had a swap that was successful, that I was maybe going towards the reference in this particular setting, then the next iteration, the fact that you're going to be proposing even swaps after the odd ones, you're not allowed to go backwards again. So this will actually maintain the direction of travel. And the only time that it will change direction is if a rejection occurs. So what this basically means is that non-reversible parallel tempering trajectories, when you do this deterministic alternation, has built-in momentum. So even though this was studied, introduced into the literature in 2001, it actually wasn't, it was still viewed with the reversible paradigm and the reversible lens where people didn't see the structure. It turns out when you let the number of chains gets very large, you get some very dramatically different behavior. So you may not be able to tell it very much in this when n is small, but when n is large, you really start to see the dynamics are no longer diffusive. You no longer get these squiggly lines, you get these straight line trajectories. And we can perform a similar analysis for non-reversible parallel tempering, and you actually can compute exactly, non-asymptotically, the round trip rate is equal to this thing, which is essentially 1/2 plus 2 times the sum of these odd ratios. And in particular, as you increase the number of chains and the mesh size of the schedule actually goes to 0, the round trip rate not only does it not only not go to 0, the round trip rate, unlike reversible parallel tempering, does not go to 0. It goes to a constant and it actually increases. So let's compare and contrast this to reversible parallel tempering. With reversible parallel tempering, the only thing that differs is this 2n factor. So in particular, non-asymptotically, for any choice of annealing schedule, for any number of chains, for any reference and target, non-reversible parallel tempering non-asymptotically dominates reversible parallel tempering. So there's no point where you should ever use reversible parallel tempering if, after seeing this topic, hopefully. In particular, like as you increase the number of chains, you get improved performance. So you don't get this penalty for having too many chains. You do get marginal gains. There's a certain point where the gains are not going to be that large, but you can guarantee that you're not going to have your performance tanked just because you increase the number of chains. Because of the fact that we can leverage this large number of chains, and this convergence to the optimality actually occurs regardless of how you pick the schedule, as long as the mesh size is small. This means that it's actually quite robust to the number of chains and the schedule that you choose. What this also means is because we don't pick up a penalty for having too few chains and we get performance by increasing the number, it actually means that this is scalable to GPUs. So before going into the more dynamics of non-reversible parallel tempering, let's see some pictures to see like how the performance differs. So if you look at the trajectories of reversible parallel tempering versus non-reversible parallel tempering, and when n is small, you can't really distinguish between the two very easily. Although we still always get usually more round trips than in non-reversible case than the reversible case. As you increase the number of chains, you start to see slightly more differentiation. There's a certain point where reversible parallel tempering is improving, and then it starts to decrease again as you increase the number of chains, whereas non-reversible parallel tempering continually increases. Let's go through this one more time. So again, look at the reversible parallel tempering starts to become more diffusive, whereas non-reversible parallel tempering starts to become more stable. And the round trips reflect this, where in the reversible case, the round trip rates increase and then go down, whereas non-reversible parallel tempering, they just uniformly increase. Again, there's marginal gains, but the performance does not deteriorate. So we can actually compute like exactly what these squiggly lines look like. So it turns out, I'm gonna avoid putting fancy or complicated math, but the punchline essentially is if you scale time by a factor of n squared. So if you pretend that if you speed up this clock at the x-axis by n squared, then the trajectories actually converge to a diffusion that is independent of the reference in the target and the annealing path itself. In particular, you can characterize this diffusion as a reflected Brownian motion on the interval 0, 1. That all sounds weird and fancy and complicated, but the real punchline here is that as the number of chains grows, the noise from the diffusivity starts to dominate. And again, this is independent of the reference in the target or the annealing path between them. So what this really means is that by modifying the reference or the target or the path, when the number of chains is large, you have very little flexibility in what can algorithmically be affected. In contrast with the non-reversible parallel tempering, if you scale time by a factor of n, so instead of increasing the clock or speeding up the clock by a factor of n squared, if it's just a factor of n, the trajectories actually start to converge to a piecewise deterministic Markov process that depends on this quantity lambda, the communication barrier that we introduced earlier. In particular, the trajectories, we can characterize them in the generators and all the fancy stuff, but the actual dynamics are essentially you go in a straight line until you hit a boundary point, or you reverse direction with rate lambda. So essentially you end up getting these straight line trajectories with random like bounces that start to happen over time. And the dynamics, so the rate at which these bounces occur increases or is governed by this capital lambda itself. So the fact that, first of all, the fact that we're scaling time by a factor of n, this means that because at any given time, remember, for parallel tempering, we have n trajectories. So this means that the performance of parallel tempering actually stabilizes. And in particular, the fact that this is not diffusive and it's a different family of paths altogether, this fundamentally differs from reversible parallel tempering, even though algorithmically it's a two-line change. Moreover, the fact that the limiting process depends on this communication barrier, which in itself depends on the reference, the target, and the path between them, this means that we have the capacity to actually do something to hopefully tune this algorithm a bit more better, in a way that you had no real leverage in the reversible case. So I've introduced this communication barrier in a couple different contexts now. We've seen this as the limiting quantity that governs the round trip rate, the maximal efficiency in terms of the round trip rate. It also is the process that it also controls the dynamics of the limiting scale process. So before we talk about what the communication barrier really is, let's talk about the local communication barrier. So the local communication barrier, I'm going to define to be the instantaneous rate of rejection. So if I have two chains that where the annealing parameters are really close to each other, we should expect the rejection rate to go to zero as the two chains, as the annealing schedule gets closer and closer to each other. So we should ask ourselves, like, what is the instantaneous rate of change? So like, what is the, if I change the annealing parameter by a little bit, how much should I expect the rejection rate to change? And then the global communication barrier turns out to be the integral of this local communication barrier across the entire path itself. So you can kind of think of this as the cumulative rejection rate along the path. So this turns out to be the quantity that governs what it means to have an optimal schedule. So we can show that the round trip rate is optimized when the rejection rates are all equal across the different chains. And the optimal schedule for that fixed number of chains is actually satisfies this quantity. So the integral of the local communication barrier from one from one annealing parameter to the next should be approximately constant and equal to capital lambda over n. So up until this point, the communication barrier is this abstract quantity that governs the theoretical analysis of parallel tempering, but it's not something that's very tangible to us. It's not something we can actually explicitly compute, but or at least up until now. But so it turns out the rejection rate, which you keep track of anyway when you're running parallel tempering just by for diagnostic reasons, we can show that turns out to be a third order error estimate of the integral of the local communication barrier. So what this means is that so the rejection rate is something that I can just approximate by running my algorithm. And what this tells us is actually the approximation of this integral. And so again, and this is true irrespective of the annealing parameters. So in particular, oh, sorry. Auto shut off. So if you sum up these rejection rates, irrespective of how you pick the schedule, when n is sufficiently large, you should actually expect to get a constant factor. And that constant will be the global communication barrier. So this is a subtle, but also really surprising point, right? Because this says that regardless of how I pick my annealing schedule, as long as I have a large number of chains, if I sum up these rejection rates, I get a constant. This means that this communication barrier is an invariant of the algorithm itself. And again, I did not tell you this was true for any schedule. So we can actually leverage this to now, well, we can get an approximation of the global communication barrier by summing up all these rejection rates. And then by taking the cumulative sum, we can build this cumulative distribution of these rejection rates. And we can do like a spline interpolation here, and then basically do an inverse mapping to figure out what these what the annealing schedule should be, so that you have a constant rejection rate. So this update it requires you to do a spline interpolation and numerical integration to solve and bisection essentially to figure out the actual optimal schedule. So because this is a one-dimensional problem, this is very cheap to do computationally. And so the algorithm essentially is we start off with a uniform schedule, then we let parallel tempering run for a certain number of iterations. We get an approximation of the rejection rates. We compute what the optimal schedule should be based off of that, and then we repeat with the next round, hopefully with a better approximation. And letting it run a bit longer every single time until you've depleted your tuning budget. And over time, as you increase the number of rounds, you actually start to get stability in this cumulative rejection rates. And the annealing schedule itself also starts to stabilize. In particular, we can see this played out in a hierarchical Bayesian model with, I think this is a 369-dimensional model with a few thousand data points. So initially, like we started off with a uniform schedule, this is in log scale. And as the rounds increases, you start to see that the annealing parameters actually start to stabilize. I think this is with 30 chains. And initially, like if you look at if you track the distribution of the rejection rates itself, so initially the rejection rates are kind of all over the place because you have a really poorly chosen schedule. And as time goes on, not only do the rejection rates stabilize, but the variance also goes to zero, meaning that we get equi rejection rates. By taking the derivative of this quantity over here, of the cumulative rejection rates, you can actually get a good approximation of the local communication barrier, which also stabilizes as the rounds increase. So this was for one example, but we can see this. In our paper, we actually benchmarked this against 16 different models, ranging from baby toy easing model to 190 something thousand dimensional phylogenetic cancer data sets. So this is we've seen it used in scale and across a variety of models, and this actually does tend to converge. We can also just see what the local communication barrier looks like. And surprisingly, it's actually not constant. And so for example, in something like the easing model, like it actually learns the points where it's higher means that the annealing path itself like was quite sensitive to small changes in beta. What this essentially means is that like our algorithm will actually learn if there's any weird phase transitions or anomalies that are occurring along the path. And oftentimes, as we see, this actually does happen. In terms of performance, if you look at it, so this is for a 30-dimensional copy number inference problem in phylogenetics. If you use a single chain with state-of-the-art methods for reversible parallel tempering, you actually end up getting very little performance because the difficulty of the problem is large. If you use reversible parallel tempering with our schedule tuning, it actually gets better performance. You start to discover more modes. And if you do non-reversible parallel tempering with our schedule tuning algorithm, you not only do you traverse more, not only does you discover the modes, but you also alternate between them reliably and often. In particular, you can, in this in particular situation, you had a very tiny posterior mode, like a very tiny mode in the posterior that because of topological constraints, a single chain just was not able to discover, whereas non-reversible parallel tempering did. Seeing this again and how it deals with multimodality and different targets. So we've seen this. So these are examples of multimodal systems that we saw that are algorithm actually giving good performance in. For example, this is for Bayesian mixture model, the easing model, copy number inference, and ODE parameter inference problem. And again, in all of these situations, not only does non-reversible parallel tempering discover modes that a single chain often can't for these hard multimodal problems, but it does it not only it makes the traversals and reliably and often. And I think you can see this in, say, the easing model, like where the one chain, like it discovers a mode and then it like miraculously goes to the next one, but then it gets trapped there, and it's alternates between these being trapped in one versus being trapped in the other. Whereas non-reversible parallel tempering actually just goes back and forth pretty regularly. Comparing this against other state-of-the-art methods that use annealing in the computational stats literature, such as AIS and SMC, our method tends to, at least right now, it's an open problem, which is better, SMC or non-reversible parallel tempering is something that I'm currently working on. But so far, we've found that non-reversible parallel tempering gives as good performance as sequential Monte Carlo with a large number of resampling steps, and often with a lower computational budget. Comparing non-reversible parallel tempering to the state-of-the-art methods in parallel tempering and how they relate to not just round trip rates, but ESS. So when we did our benchmarking against the other state-of-the-art methods for parallel tempering that were based off the reversible paradigm, I think these were methods that came out in 2011 and 2014. We found about a 10 to 100 order magnitude difference in ESS per second. So far I've talked about all the applications of our own work that we did, but that's not as satisfying. But so this actually has been used in practice, and I think the coolest application, in my personal opinion, so far has been through the Event Horizon Telescope. So the Event Horizon Telescope was the collaboration that developed the photo of the black hole that came out in 2019. So in the background, to actually process the photograph required parallel tempering. And this is the implementation that, using the implementation that they did in 2019, that's how they were able to get this original photograph that came out a few years ago. So in 2020, they actually implemented our work, and they were able to recreate the results of the original photograph, which originally took, I think, on the order of like 5-ish days. This was work done at the Perimeter Institute with access to all of Compute Canada and their supercomputer. So with about 128 chains, they were able to recreate the results of the original photograph in about 2% of the computational budget in about 45 minutes. And so the speed up is quite nice, but it's not, but it was also the fact that they were able to discover posterior modes for the photograph that were about, that were just far more likely, and it was making the traversals much more often. Paul Tita, who is now doing a postdoc at Harvard, actually did, for his PhD thesis, benchmarked our method versus the state-of-the-art methods across not just non-reversible parallel tempering, but with other exploration kernels as well. So the computational advancements that the Event Horizon Telescope got from our method in 2020, they allowed them to tackle new problems that were computationally intractable before. So last year, they released this new updated version of the photograph where they discovered magnetic polarization, which was not something that, this would actually use the same data, but they were not, so it's not like they discovered new, this was using the same data that they had in 2019, but just, again, the computational limitations but they were now able to tackle problems because of the advancements that came from our algorithm. The BC Cancer Research Center and MSK Cancer Research Center in New York used non-reversible parallel tempering to actually model time series of single-celled cancer genomes. So they were able to use non-reversible parallel tempering to study the phylogenetic tree of the phylogenetic evolutionary tree that studies how the evolutionary structure of cancer, essentially. Google Research used non-reversible parallel tempering last year to tackle ill-conditioned Bayesian inverse problems applied to nuclear fusion. And I think the most exciting aspect of this is that, again, parallel tempering isn't an algorithm by itself. It's more of like a meta algorithm. So the input is a locally well-mixing MCMC algorithm plus access to multiple cores. And the output is a better well-mixing, globally well-mixing MCMC algorithm. So in particular, because of the generality, we have not made any assumptions on the state spaces or the actual distributions themselves. That mean that this is amenable to, or this is really well suited for using as an inference engine for probabilistic programming languages. So far, this has been used by Blang for phylogenetic inference and Themis for for astrophysics. Turing.jl as well as TensorFlow probability have implemented non-reversible, the non-reversible scheme, but they haven't implemented we're currently in talks with them to actually implement our schedule tuning algorithm as well. So far I've talked about non-reversible parallel tempering, and hopefully I've demonstrated that this is a useful algorithm. But again, this capital lambda, that communication barrier just kept on popping up. And again, that number represents somewhat of an intrinsic limitation of the algorithm itself. So it's something that no matter how many chains that you have, no matter how clever you are with the schedule, you can't overcome it. So if you have a problem where the communication barrier is really large, this means that you should just expect a bad performance, right? Or you might need computational resources that are just unreasonable, and that's essentially will kill off the efficiency of your algorithm. So the rest of the talk, I want to discuss how we can find strategies of actually reducing this global communication barrier, which represents the limitation of PT itself. So first of all, this communication barrier, remember, is approximately equal to the sum of the rejection rates along the path. And the rejection rates, then we should ask ourselves, what are those? So you can interpret the rejection rate as a measure of the overlap between two distributions. So when the overlap between two distributions is quite large, it's quite small. Oh wait, when the overlap is large, the rejection rate is approximately 0. When the overlap is small, you should have the rejection rate approximately equal to 1. So in particular, the rejection rate can be viewed as a divergence between two distributions. So when the two distributions are close to each other and it's equal to 0 if and only if the two distributions are exactly equal and it's equal to 1 otherwise. So it's not quite the total variation distance because that is the direct measure of the overlap. You can kind of show that it's equal to the total variation distance between, so if you have the rejection rate between two distributions P and Q, then this actually, and we can show it equals the total variation distance between P times Q minus Q times P. So it measures the overlap of the diagonal. So it's not quite a metric but it doesn't satisfy triangle inequality, but it has some nice properties that we can play with. In particular, if I have a general path, then so far I've been assuming a linear path, but if I have a general path, I can redefine the notion of a local communication barrier as the instantaneous rate of rejection along the path itself. And again, we can extend the definition that we had for the linear path to the nonlinear one by just integrating this local communication barrier across the path. So for a general annealing path, this local and global communication barrier should have the same interpretation as the linear path case. And we can show that under certain mild regularity assumptions on the path, that are mostly just needs to be twice differentiable and like sufficiently integrable. The optimal performance of parallel tempering, the round trip rates are still governed by this communication barrier for a general path. So the question now becomes like, can you do better? And then the linear path, and turns out, yes. So I think this is most notable in situations where the reference and the distribution, the reference and the target are nearly mutually singular from each other. So there's very little overlap. And that's where you should expect the communication barrier to be large. So in particular, if you notice that in this case where the reference is, and reference and the target are just translations of each other, the linear path ends up looking like a translation path along the two. And turns out the optimal path turns out to be something that looks like this, where we want to take mass from the reference to the target while simultaneously maximizing the overlap between the two. The linear path makes no effort to maximize this overlap. It's just making sure the mass is transported. So we're going to see where this optimized path came from in a second, but that's essentially the mental image that we're working towards right now. Before going into more of the how we get there, I think it's first thinking about the geometric aspects of these paths. So from now on, we're going to assume that our reference and our target live within some parametric family of densities. So I've used the letter M to denote a manifold. If you know what a manifold is, great. If you don't, just think of a parametric family. So we're going to have this M, this parametric family is going to be parameterized by the eta. So essentially, annealing paths in this parametric family that connect between the reference and the target are going to now be in one-to-one correspondence with paths in parameter space eta, which are now vectors. So this is you can now think of paths in our Euclidean space, whereas here you think of pathodistributions. So the natural thing to ask, well, what does it mean for a path to be differentiable? So we want to have some smoothness properties. So we'll say that a path is differentiable with velocity equal to the derivative of its log likelihood. So it turns out log scale is where you want to live when you're dealing with probability distributions. So we can define differentiability of the annealing path, and turns out to be with respect to the differentiability of the path in this parameter space by using chain rule. So if you use chain rule and you substitute in pi beta equals if you substitute in pi beta equals p of the path in parameter space, you end up getting that the gradients of, or the velocity equals the gradient of the path times the score function, essentially. So this S of eta is some correction factor, essentially, that allows you to translate between the velocity of the annealing path and the velocity of this parameterized path. So when you have a velocity, the natural question becomes, what is the speed? So the velocity represents the direction of travel as well as the speed. So the speed would be the length of the path of the velocity itself. So the length, we can be a bit looser here. So it's not necessarily a length in the Euclidean sense, but there is a way of describing this local communication barrier that we described earlier as the instantaneous rate of rejection as the speed of this velocity curve. And again, when you are integrating the speed along a path, you end up getting the length of the path. So one point to note is that this norm, I wrote the equation down here just to show you what it is, but don't stare too long at it, in my personal opinion. The main thing to take from it is not quadratic. So it's not necessarily a quadratic norm, but it satisfies all the conditions of the norm in a reasonable sense. And it smoothly varies with eta as well. So again, what we can now reinterpret this global communication barrier as the length of the path. So what we want to do now is, so again, different paths correspond to different parallel tempering algorithms. And the efficiency of the algorithm corresponds to the length of the path itself. So what this means is that we can tune, given a collection of paths to pick from, we can actually tune parallel tempering, like so we can resolve the issue of what is the optimal path by figuring out what are the geodesics. So what is the length minimizing curve essentially? And the length is in terms of this geometry, but more so, this is the cool thing I think that the punchline to take from this is that we've transformed the problem of optimizing parallel tempering into the problem of finding geodesics in these vector valued curves.
Just about 5 minutes, Saif.
Sounds good. So in particular, you can show that this communication barrier, if you either can upper bound this by the Fisher information. The details aren't particularly relevant, but the Fisher information is a Riemannian manifold. You can view this as a Riemannian metric. So this is actually a quadratic norm. And in some situations, we can actually explicitly compute this. So the concrete example to look at is the Gaussians. So the Gaussians, if you pretend, for example, right now that the Gaussians are the mean, you can parameterize them in terms of the mean and their standard deviation. So if I give me a mu and a sigma, you can tell me what the distribution is itself. You can explicitly compute what these quantities need to be. And I'm just going to go straight to the punchline. So the Gaussians, you can now parameterize them in terms of the upper half plane, where the x-axis is mu and the y-axis is sigma. And this turns out to have a hyperbolic geometry. Again, you don't need to know what that is, but know that in this case, the linear path corresponds to this straight line. And the geodesics mathematicians have explicitly computed turn out to be the semicircle trajectories. And in particular, the length of the linear path turns out to be like on the order of z, where z is the distance between the means, whereas the geodesic length turns out to be order log of z. The main thing to note, though, is that as you increase so when the difficulty of the problem is large, so when z is large means that the two distributions they have very little overlap between the two, you've effectively gained an exponential order gain in performance by just picking a better path. And this motivates like what happens when you have nearly mutually singular reference and target distributions, which happens quite often. And it allows us to design a new family of paths, like by studying the structure that we got from the Gaussians. So we can construct, given a reference and a target, we can actually design the exponential family generated by the reference and the target. So the linear path would correspond to paths where eta naught plus eta 1 would equal to 1. But when eta naught and eta 1 are, when they're close to 0, this actually allows for the distributions to be flatter. So what this means is that we can construct paths now that go from the reference to the target while simultaneously flattening and contracting. I'm going to skip over a lot of the details, but essentially, like we can now design annealing paths in this particular concrete family that's generated by the reference and the target. And we can construct these paths using, or we can approximate them using splines, where we can actually optimize over the knots. And we have, in our paper, we describe how you can actually do this tractably. So as you let the algorithm run, you'll actually start to discover the geodesics. So the target corresponds to this point over here, and the reference corresponds to this point over here. The linear path is a straight line. These geodesic, like these splines for different values, for a different number of knots, actually learns the approximate geodesic. And this is not something we inputted. This is actually it discovered itself. And you can see this in terms of the actual, you can see this in the number of round trips that you observe. So for example, in the Gaussian, as you increase, if you're comparing the total number of round trips as the number of iterations increases, in the early stages, there's because the tuning procedure is actually learning the path itself. It doesn't generate a lot of round trips. But reversible parallel tempering and non-reversible parallel tempering both don't generate many. This was with 50 chains with a global communication barrier of 113. The resultant communication barrier ended up being around 7. So you notice how, the dotted line over here represents the maximal theoretical efficiency that arises from using parallel tempering with just a linear path. Whereas when you even just add the flexibility of one additional knot, you can gain significant performance gains and that shatter the communication barrier that arose from linear paths itself. And we have benchmarked this for a beta binomial model as well as a mixture model. I think this was a 94-dimensional mixture model. So yeah, so this actually does work in practice. And so yeah, in summary, non-reversible parallel tempering dominates reversible parallel tempering for non-asymptotically for any number of chains and any annealing schedule. We've been able to optimally characterize the annealing schedule that maximizes the round trip rate. Non-reversible parallel tempering can scale to GPUs and massively distributed hardware. We've also developed a natural efficiency metrics and diagnostic tools that are useful for practitioners and that make it easy to implement. We made very little structural assumption. We make no structural assumptions on the model or the state space, so we get stronger results with less assumptions. And we also developed an efficient black box algorithm that has been, for both schedule and path tuning, that has been used at scale already. Thank you.
Thank you so much, Saif. There was so much there, and you did so well explaining it to us. I'll just ask, are there any questions in the room?
It's a lot of information in a short amount of time.
Yeah, you've done well. Yeah, Matt, do you want to come up and ask? At least then Saif can see you in the camera. Yeah.
Sure. Hi, thanks for that. It was a really, really good talk. I was just wondering, maybe it's a totally off mark comment, but with the parallel tempering, the non-reversible sort of structure that you had, it kind of felt like everything had the same unit velocity as it was moving in the one direction, like they're just the regular algorithm. And then this alternative one that you have, the optimized path, is there some kind of a connection to having like a speed up of velocity as you're moving in that other framework?
Yeah, so I actually shoved that under the rug right now. So it turns out there is reparameterizations of your path. There's a one-to-one correspondence between reparameterizations and the schedule that you generate itself. So if you assume that your schedule is always generated uniformly, then if you reparameterize your path, then the schedule will change accordingly. So you can show that the speed of your path corresponds to, so the optimal schedule turns out to correspond to the reparameterization of your path that gives you the constant speed, which is, I can go into more details essentially if you want, but what this means is that, yeah, so in the actual dynamics that I showed over there, so I can pull it up here. Yeah, so when I said that it's controlled truly by like this global communication barrier, I kind of lied to you. It's actually controlled by the local communication barrier, which is the speed. So you would essentially have, like, you would be maintaining a certain direction and you would reverse direction according to the local communication barrier. But if you've chosen your schedule to be the optimal one, the reparameterization of your beta space will ensure that the local communication barrier actually equals the global communication barrier, because that's the constant speed path. So yeah, there's a cool geometric connections here that I just didn't have time to go through because I also didn't want to scare people off of geometry.
We promise we're not scared. Lawrence, do you want to ask your question? If you unmute yourself.
Thanks, Josh, and thanks, Saif. That was an amazingly inspiring talk. I had a couple of questions right there pretty quick. The first one is, you did mention a quick comparison. Sorry, I'll turn my video on. You did mention a quick comparison between non-reversible PT and SMC, and I'm jumping on that because that's something I've been asked recently. So not with non-reversible. So I'm really interested in the flavor of SMC you used there, if it's a fixed or a adaptive annealing schedule. And the second question is for the optimized annealing schedule, which is extremely interesting. Did you is there any restrictions on the kind of Markov chains you can have? The notation passed by me a bit quickly, but I did notice that you had a D for dimension. Is there a fixed dimension, or is there any kind of restriction at all on the kind of Markov chains you have there?
Okay, so first I'll go into the SMC question. So we use adaptive SMC, from Zhu et al. In 2016. So that's, I think, right now currently the state of the art.
Yep.
Yeah. So this is actually a question that I'm currently answering right now and hoping to write a paper in the next few months on actually benchmarking and so right now, both SMC, adaptive SMC and non-reversible parallel tempering, they use the same ingredients, and they essentially have a lot of similarities, and they both are very parallel, and they both are in practice end up giving very similar results. So the main question that I want to really answer is when you should use one versus the other. So first of all, it's a very open problem. But we found at least non-reversible parallel tempering tends to be competitive with the state of the art with SMC right now. In some sense, you can think of non-reversible parallel tempering as a horizontal algorithm where you at any given time have n particles at different annealing parameters, and you're over time building up the number of distributions. So every time say a round trip occurs, you can say maybe you've observed one new source of randomness into the target. So the total number of round trips over time, you can kind of, so as you increase time, you're slowly accumulating the number of round trips over time. Whereas with SMC, you kind of start off with your initial population cloud at the reference, and then you're slowly building up. So you're constantly going from the reference to the target in a bottom up approach. Whereas with SPT, you're going in a horizontal approach. And in one way, you can think of SMC as a smoothed out version of importance sampling. Whereas parallel tempering, you can think of it as a smoothed out version of metropolis Hastings. So the real fundamental question you can ask is when should you use metropolis Hastings versus importance sampling? And that is, I don't really have a good answer for that. But hopefully it gives you some intuition. And I forget the second question again. Can you briefly remind me again?
That was a fantastic answer to the first question, thanks. And second question was on the annealing schedule. Is it any restrictions such as fixed dimension or anything like that for the Markov chain?
No. So the assumption that we have on the Markov chain itself, to make the analysis tractable, we assumed we had this thing called the efficient local exploration assumption, which essentially we didn't assume that you get ID samples from the target itself or from the annealing distributions themselves. But we assume that you get ID samples from the likelihood function, which essentially means that even if you have a bimodal distribution, the likelihood is actually would be unimodal. So it's what we really are, so essentially what we're really assuming fundamentally is that you have locally well mixing. So whatever Markov chain that you have, like when you have a worse exploration kernel versus a better one, you should pick up a penalty for that. And the penalty comes from the mixing within a mode. So you can kind of think of the local exploration move as it measures the efficiency within a mode, and the communication step allows you to measure efficiency between modes. And when I'm proposing a swap between two states that are, say, at different modes from each other, the swaps actually do not see the location. They just see how likely the modes are. So if if I have, like, say, two modes over here, and I have one state here and one state here, both in the center, then they both are equally likely. So a swap will actually occur very easily. So that's essentially the assumption that we really need on the Markov chain itself. So just locally well mixing. In terms of dimension, the global communication barrier turns out to be a sufficient statistic. I didn't really talk about the high dimensional scaling, but we did the analysis. And so you can show that the communication barrier, it encapsulates all the information about the reference, the target, the path, the state space, the dimensionality of the model, et cetera, into that one number that is relevant for parallel tempering itself. So for example, if you have like a target that maybe like has IAD copies of itself and you're letting the dimensionality go to infinity, you can show that the communication barrier scales according to root D times the Fisher-Rao length. We can actually compute that itself. So we can compute the constants as well as the scaling factor, but essentially the communication barrier is the number that measures everything. We put dimensions and like data points here just to mainly show that it actually works in real data as well, not just like these toy models that we built, but the dimension is kind of incorporated into the communication barrier.
That's great. Thanks for that answer, Saif. And thanks again.
Thank you.
Yeah, thank you so much, Saif. We might call it there just because it is 2:10 your time.
I'm fine, right? If there's more questions, I'm more than happy to answer.
Yeah, okay. Chris has got a question, but I just want to invite anyone who needs to go, feel free to. I don't want to keep you hostage in the room. Chris, do you want to ask from there? Brody, do you want to ask your question first?
Yeah, sure. I just had a quick, firstly, that was a really good talk and really well explained. And it kind of made me, excited to, I shouldn't, but anyway, like I want to implement it, but then at the same time, it's like, shouldn't be doing new things. But because of that, I thought the question that might be a good one to ask would be about getting a sense of implementing the algorithm. And this is more, I guess, generally a question about parallel tempering, not necessarily the improvements, but I think you explained the improvements really well. So with parallel tempering, and you said kind of the input is a locally well mixing chain. So I assume then you're doing sort of a bunch of Metropolis Hastings steps for each chain, and then every so often you're asking, do I want to swap the components? Is that the right sense of that?
So it could be whatever your favorite MCMC algorithm is, and that your problem should dictate what the local exploration move should be. So for example, if you are, it could be like it could be random walk Metropolis, it could be HMC, it could be Langevin, but if you're in a non-Euclidean setting, maybe like you have some other MCMC move that you've constructed for your like whatever weird problem that you have. So parallel tempering is, again, it works generally for, we kind of avoided talking about the exploration move itself because of the fact that it is so problem specific. So that's why we focus our attention on the communication step.
Yeah. So I guess it's not about how do I do the local exploration, but just a sense of, like, let's say I'm doing garden variety MCMC. I'm not doing sort of one MCMC step and then one do I want to swap step, right? Am I?
So yeah, it turns out we actually did this analysis in our paper as well. Like I would recommend checking it out.
Yeah, okay.
But so you can ask yourself, okay, I have a fixed computational budget. Like I have this many, like I say 10,000 like MCMC steps that I can do. And I could either opt to have a lot of MCMC moves between swaps and have good like quality like states to propose swaps with, or I could do like, so I could do a few swaps with high quality swaps, or I could do like a lot of very low quality swaps. And turns out there's both theoretical and experimental reasons to suggest that you should go for the latter. The general rule is that you should do the most swaps that you can within your computational budget.
Yeah.
So if swaps are cheap, do as many of them as possible. And yeah, that's basically, there's actually was a paper that came out in I'm gonna like butcher the authors and everything, so I'm just not even gonna say, but there was it was measuring the scaling properties of parallel tempering in a infinite swapping regime. And it turns out like you get better performance by having more swaps. That's just
okay. And then one other very simple implementational question, just to make sure I was understanding it right. So when you said like these are still MH swaps that you're doing, so essentially you just mean you're using your likelihood that's implied by kind of the product of all the different components having their own tempered thing. And you're just saying after I swapped it, how did those parameter changes? Yeah, cool. Okay. Yep. Thanks for that. It was really good talk.
Yeah, we just got a question from Chris.
Can I also just make one more comment on Brody's question?
Of course.
So even though one of the other things we studied in our paper was, so the effect of the different quality of again, you could have either a high number of like low quality swap, a high number of low quality swaps or a low number of high quality swaps. And we found that the estimates of the rejection rates, the communication barrier, the quantities that actually control the tuning of the algorithm itself, they were really robust to that. So even though the number of round trips actually generally do improve, and the quality of the algorithm does improve by having a high number of cheap swaps, we found that yeah, it does not impact the actual tuning of the algorithm itself. So that's another reason why you should do it.
Hi, Saifuddin. This is Chris from QUT here. So I guess you're not going to be going to bed tonight, but that's okay. So I had a question actually about the tuning of the within MCMC proposals, within chain proposals. So I think it's important to talk about because you mentioned, oh, just use your favorite MCMC algorithm, but pretty much all MCMC algorithms involve some kind of tuning. And so now we've gone from tuning one chain to having to tune, say, 50 chains, which is, maybe that's a little bit daunting. So do you have any advice on how one should do this tuning and if the results of the performance might be sensitive to this tuning?
Yeah, the unfortunate answer to that is you pray. You hope that at least that there's some smoothness within the tuning parameters themselves across the different chains. So like if say if you're using HMC, the tuning parameters of HMC for pi 0.9 should be similar to pi 0.91. So that's, it's also like from round to round, like if you are doing whatever kind of tuning, you should start the tuning where you finished the round before. So instead of having to restart from scratch, you should just be continuing where you left off. Mm-hmm. But this is an open problem right now. This is something that I would say, like specifically with something like HMC, which is probably the most popularly used kernel right now. There is no satisfying solution to tuning this. And I think a big part of that is because the way that people have developed tuning guidelines for HMC have not been with this parallel setting in mind. So the fact that, I think like our paper right now is more of a demonstration that this is now a problem people should be starting to think about a little bit more.
Yeah.
In the implementations for the Event Horizon Telescope, and right now I've been also talking with Turing.jl, the developers of their parallel tempering algorithm. They also don't really have, so there's a lot of hacky things that people have been doing, but there's no satisfying solution.
Okay, sure. And my other question was, do you recycle the information from the other chains when you do your final inference? So, for example, just do important sampling to reweight the samples from the other chains to improve the performance of the expectation that you want to compute?
So we found in general that does not add a lot of value to the final solution. So we did try this, and but it didn't really give us anything particularly meaningful. So yeah, that would be, again, not a particularly satisfying answer, but I would say
Okay.
there isn't much
All
of
right. Sure.
there's not much to gain, at least from my point of view so far.
Yeah, okay, thanks for that.
Yeah, I'll just make a quick comment that I can't remember who the authors are, but the paper that is tuning HMC within SMC might have some translatable ideas for tuning HMC within non-reversible parallel tempering. Seeing as you are there, I did have one more question, Saif, if you're willing to answer. So you talked about choosing these paths between reference and target distribution. But if I'm a practitioner and I'm setting up a parallel tempering algorithm, and I've got my target, but my reference, I potentially could choose any distribution so long as it has the correct support. At what point should I stop trying to fiddle or tune the reference distribution and start trying to use your tuning for the paths between the two distributions?
So excellent question. It's just actually something one of the grad students at UBC and I have been working on for the last few months. So you can kind of think of, so yeah, if you have like, so far in our analysis, we've been assuming that the reference is fixed, but it's very natural to assume that the reference is a lot, you have a family of reference to pick from, and you want to pick the reference that is closest. And in some sense, you can think, again, because of the geometric view of what the communication barrier is, you can interpret it as the length of the path. So in some sense, you want to find the reference that is tractable and easy to solve, that is closest to the target as possible, so that the length is minimized, which kind of has a flavor of variational inference. Variational inference where you're tuning not the KL divergence, but this communication barrier, and then you're using parallel tempering to essentially make the correction factor. So this is actually a paper that we will hopefully be submitting in for NeurIPS in a couple of months. So look out for that in a couple of months.
Yeah, please let us know. We'd be very interested to look at it. Lawrence says Chopin is probably the paper. I just want to thank you again, Saif. You've been very generous with your time. It's been so great to hear from you. And again, you packed so much in. And I know that like I've learnt things, even though I've seen various versions of this talk a few times. I guess just one more round of applause from Saif, and just acknowledge that when everyone applauds, Maisie, the guide dog in training, will probably stand up, and technically it'll be a standing ovation. So thank you so much. She got up the first time. Thank you so much. Safe home.